Electric shock is the physiological reaction or injury caused by electric current passing through the body. Typically, the expression is used to describe an injurious exposure to electricity. It occurs upon contact of a body part with any source of electricity that causes a sufficient current through the skin, muscles, or hair. Very small currents can be imperceptible. Larger current passing through the body may make it impossible for a shock victim to let go of an energized object. Still larger currents can cause fibrillation of the heart and damage to tissues. Death caused by an electric shock is called electrocution. An electrical injury has many consequences to a body as the electrical currents can travel through the nervous system and burn out tissue in patches. Along the way, this can leave bizarre symptoms anywhere on the body and may lead to complex regional pain syndrome. Wiring or other metalwork which is at a hazardous voltage which can constitute a risk of electric shock is called live, as in, live wire. Shocks can be caused by direct or indirect contact. Contact with an exposed conductive part under fault conditions is called indirect contact. IEC requires certain degrees of ingress protection against direct contact. Indirect contact protections can be achieved by earth equipotential bonding and automatic disconnection of supply by using fuses, for example. Magnitude. The minimum current a human can feel depends on the current type as well as frequency. For AC, a person can feel at least 1 mA of AC at 60 Hz, while at least 5 mA for DC, at around 10 mA. AC current passing through the arm of a 68 kg human can cause powerful muscle contractions. The victim is unable to voluntarily control muscles and cannot release an electrified object. This is known as the let-go threshold, and is a criterion for shock hazard in electrical regulations. The current may, if it is high enough, cause tissue damage or fibrillation which leads to cardiac arrest. More than 30 mA of AC or 300 to 500 mA of DC can cause fibrillation. A sustained electric shock from AC at 120 V, 60 Hz is an especially dangerous source of ventricular fibrillation because it usually exceeds the let-go threshold, while not delivering enough initial energy to propel the person away from the source. However, the potential seriousness of the shock depends on paths through the body that the currents take. If the voltage is less than 200 V, then the human skin, more precisely the stratum corneum, is the main contributor to the impedance of the body. In the case of a macro shock, the passing of current between two contact points on the skin. The characteristics of the skin are non-linear. However, if the voltage is above 450 to 600 V, then dielectric breakdown of the skin occurs. The protection offered by the skin is lowered by perspiration, and this is accelerated if electricity causes muscles to contract above the let-go threshold for a sustained period of time. If an electrical circuit is established by electrodes introduced in the body, bypassing the skin, then the potential for lethality is much higher if a circuit through the heart is established. This is known as a microshock. Currents of only 10 microamperes can be sufficient to cause fibrillation in this case. Signs and symptoms. Burns. Heating due to resistance can cause extensive and deep burns. Voltage levels of 500 to 1000 volts tend to cause internal burns due to the large energy available from the source. Damage due to current is through tissue heating. For most cases of high-energy electrical trauma, the Joule heating in the deeper tissues along the extremity will reach damaging temperatures in a few seconds. Ventricular fibrillation. A domestic power supply voltage, 50 or 60 Hz alternating current through the chest for a fraction of a second may induce ventricular fibrillation at currents as low as 30 mA. With direct current, 300 to 500 mA is required. If the current has a direct pathway to the heart, a much lower current of less than 1 mA can cause fibrillation. If not immediately treated by defibrillation, Fibrillation is usually lethal because all of the heart muscle fibers move independently instead of in the coordinated pulses needed to pump blood and maintain circulation. Above 200 mA, muscle contractions are so strong that the heart muscles cannot move at all, but these conditions prevent fibrillation. Neurological effects. Current can cause interference with nervous control, especially over the heart and lungs. Repeated or severe electric shock which does not lead to death has been shown to cause neuropathy. Recent research has found that functional differences in neural activation during spatial working memory and implicit learning oculomotor tasks have been identified in electrical shock victims. When the current path is through the head, it appears that, with sufficient current applied, loss of consciousness almost always occurs swiftly. Arc flash hazards. OSHA found that up to 80% of its electrical injuries involve thermal burns due to arcing faults. The arc flash in an electrical fault produces the same type of light radiation from which electric welders protect themselves using face shields with dark glass, heavy leather gloves, and full coverage clothing. The heat produced may cause severe burns, especially on unprotected flesh. The arc blast produced by vaporizing metallic components can break bones and damage internal organs. The degree of hazard present at a particular location can be determined by a detailed analysis of the electrical system, and appropriate protection worn if the electrical work must be performed with the electricity on. Pathophysiology. Body resistance. The voltage necessary for electrocution depends on the current through the body and the duration of the current. Ohm's law states that the current drawn depends on the resistance of the body. The resistance of human skin varies from person to person and fluctuates between different times of day. The NIOSH states, under dry conditions, the resistance offered by the human body may be as high as 100,000 ohms. Wet or broken skin may drop the body's resistance to 1,000 ohms, adding that high-voltage electrical energy quickly breaks down human skin, reducing the human body's resistance to 500 ohms. The International Electrotechnical Commission gives the following values for the total body impedance of a hand-to-hand circuit for dry skin. Large contact areas, 50 Hz AC currents. Voltage current characteristic of human skin. The voltage current characteristic of human skin is nonlinear and depends on many factors such as intensity, duration, history, and frequency of the electrical stimulus. Sweat gland activity, temperature, and individual variation also influence the voltage current characteristic of skin. In addition to nonlinearity, skin impedance exhibits asymmetric and time-varying properties. These properties can be modeled with reasonable accuracy. Resistance measurements made at low voltage using a standard ohm meter do not accurately represent the impedance of human skin over a significant range of conditions. For sinusoidal electrical stimulation less than 10 volts, the skin voltage current characteristic is quasi-linear. Over time, electrical characteristics can become nonlinear. The time required varies from seconds to minutes, depending on stimulus, electrode placement, and individual characteristics. Between 10 volts and about 30 volts, skin exhibits nonlinear but symmetric electrical characteristics. Above 20 volts, electrical characteristics are both nonlinear and symmetric. Skin conductance can increase by several orders of magnitude in milliseconds. This should not be confused with dielectric breakdown, which occurs at hundreds of volts. For these reasons, current flow cannot be accurately calculated by simply applying Ohm's law using a fixed resistance model. Point of entry macroshock. Current across intact skin and through the body. Current from arm to arm, or between an arm and a foot, is likely to traverse the heart. Therefore it is much more dangerous than current between a leg and the ground. This type of shock by definition must pass into the body through the skin. Microshock. Very small current source with a pathway directly connected to the heart tissue. The shock is required to be administered from inside the skin, directly to the heart, i.e., a pacemaker lead, or a guide wire, conductive catheter etc., connected to a source of current. This is a largely theoretical hazard, as modern devices used in these situations include protections against such currents. Lethality. Electrocution. The term electrocution, coined about the time of the first use of the electric chair in 1890, originally referred only to electrical execution and not to accidental or suicidal electrical deaths. However, since no English word was available for non-judicial deaths due to electric shock, the word electrocution eventually took over as a description of all circumstances of electrical death. Factors in lethality of electric shock. The lethality of an electric shock is dependent on several variables. Current. The higher the current, the more likely it is lethal. Since current is proportional to voltage when resistance is fixed, high voltage is an indirect risk for producing higher currents. Duration. The longer the duration, the more likely it is lethal. Safety switches may limit time of current flow. Pathway. If current flows through the heart muscle, it is more likely to be lethal. High voltage. In addition to greater current flow, high voltage may cause dielectric breakdown at the skin, thus lowering skin resistance and allowing further increased current flow. Other issues affecting lethality are frequency, which is an issue in causing cardiac arrest or muscular spasms. Very high-frequency electric current causes tissue burning, but does not penetrate the body far enough to cause cardiac arrest. Also important is the pathway. If the current passes through the chest or head, there is an increased chance of death. From a main circuit or power distribution panel, the damage is more likely to be internal, leading to cardiac arrest. Another factor is that cardiac tissue has a chronic C of about 3 milliseconds. So electricity at frequencies of higher than about 333 Hz requires more current to cause fibrillation than is required at lower frequencies. The comparison between the dangers of alternating current at typical power transmission frequencies and direct current has been a subject of debate ever since the War of Currents in the 1880s. Animal experiments conducted during this time suggested that alternating current was about twice as dangerous as direct current per unit of current flow. It is sometimes suggested that human lethality is most common with alternating current at 100 to 250 volts. However, death has occurred below this range, with supplies as low as 42 volts. Assuming a steady current flow, shocks above 2,700 volts are often fatal, with those above 11,000 volts being usually fatal. Shocks with voltages over 40,000 volts are almost invariably fatal. However, Harry F. McGrew came into direct contact with a 340,000-volt transmission line in Huntington Canyon, Utah, and survived. According to the Guinness Book of World Records, this is the largest known electric shock that was survived. Brian Lattisaw also survived a 230,000-volt shock in Griffith Park, Los Angeles, according to Guinness. Epidemiology. There were 550 electrocutions in the U.S. in 1993, 2.1 deaths per million inhabitants. At that time, the incidence of electrocutions was decreasing. Electrocutions in the workplace make up the majority of these fatalities. From 1980 to 1992, an average of 411 workers were killed each year by electrocution. A recent study conducted by the National Coroner's Information System in Australia has revealed 321 close-case fatalities that had been reported to Australian coroners where a person died from electrocution between July 2000 and October 2011. In Sweden, Denmark, Finland and Norway, the number of electric deaths per million inhabitants was 0.6, 0.3, 0.3 and 0.2, respectively. In years 2007 to 2011, many people survive electrical trauma only to find a host of injuries including loss of consciousness, seizures, aphasia, visual disturbances, headaches, tinnitus, paresis, and memory disturbances. Even without visible burns, electric shock survivors may be faced with long-term muscular pain and discomfort, fatigue, headache, problems with peripheral nerve conduction and sensation, inadequate balance and coordination, among other symptoms. Electrical injury can lead to problems with neurocognitive function, affecting speed of mental processing, attention, concentration, and memory. The high frequency of psychological problems is well established and may be multifactorial. As with any traumatic and life-threatening experience, electrical injury may result in post-traumatic psychiatric disorders. There exist several non-profit research institutes that coordinate rehabilitation strategies for electrical injury survivors by connecting them with clinicians that specialize in diagnosis and treatment of various traumas that arise as a result of electrical injury.